Hello and welcome back to the Juniper JNCIS Enterprise Routing and Switching Training Series. In this section, we will be talking about OSPF, or Open Shortest Path First Routing Protocol. In this section, we will be talking about OSPF, or Open Shortest Path First Routing Protocol. We will explain the concepts, operation, and functionality of OSPF, as well as some troubleshooting tactics. So let's jump in and get started. OSPF is an Interior Gateway Protocol, or IGP, that routes packets within a single autonomous system. OSPF uses link state information to make routing decisions, making routing calculations using the Open Shortest Path First algorithm, also referred to as Dijkstra's algorithm. Link state advertisements. Each router running OSPF floods link state advertisements through the autonomous system or area that contains information about the router's attached interface and routing metrics. Each router uses the information in these link state advertisements to calculate the least cost path to each network and create a routing table for the protocol. Link state database. After the prefix from the neighbors and the neighbor's information is known by the flooding of LSAs, another task of OSPF protocol is to maintain the database of all prefixes which were discovered during the flooding. In other words, to maintain the link state database, or LSDB, these LSDBs are stored in a topological order and are maintained to calculate the SPF algorithm. Apart from the prefixes information of routers, these LSDBs include other details such as the advertising router's ID, its attached networks, and neighboring routers, and the cost associated with those networks or neighbors. One key point to remember, an OSPF area must have the identical routing information in the LSDB. The SPF algorithm, or Dijkstra's algorithm, performs shortest path first calculation by creating a tree of shortest paths incrementally and picking the best candidate from that tree. The results of this calculation are then handed to the router's routing table for the actual forwarding of packets. The current version of the JNCIS ENT covers only OSPF version 2. OSPF version 3 has IP version 6 capability and has some added advantages with respect to IP version 6, but it's not covered in this course or this exam. So we have 5 different types of OSPF version 2 packets. Type 1 is hello, Type 2 database descriptor, Type 3 link state request, Type 4 link state update, and Type 5 link state acknowledgement. So let's go through each of these types and explain how they work. Hello type. Routers exchange hellos every 10 seconds by default. They use multicast IP 224.0.0.5 between DR other and DR router and 224.0.0.6 between DR and the BDR. A hello packet has both mandatory and optional fields. Number 1, the network mask. All the routers with IP prefixes advertised must have the same subnet mask. On Juniper, the network mask needs to be the same even between point-to-point links, unlike Cisco. Hello interval. The time interval the router should send hello packets. By default, it will be 10 seconds. And then we have the dead interval. This is the time agreement on which the adjacency needs to be removed from the adjacent router. Options. Ability to become a stub area. This is an 8-bit field. And then we have router priority. What is the priority of the OSPF router to become master, slave, or participate in the initial database? Designated router. The router that becomes the DR, or designated router, is evaluated on priority. Highest will take precedence if the priority is the same. Then highest RID will win. Then we have Backup Designated Router, or BDR. And then we have the neighbor. All routers next to each other participate in OSPF and are therefore neighbors. Next, we have Type 2, the database descriptor. This will determine which router will be in charge of the database synchronization and actually transferring the LSA headers between the two systems. The router with the highest RID will become the master and will be responsible for the database synchronization, and the other router will be the slave. It is not mandatory that this router be the designated router. Sequence number will be maintained by the master. Now let's talk a little bit about the details of the DD packet field. First, we have the OSPF header. This header is composed of 24 bytes. And then we have the sequence number. This is ensured by the highest RID, and if it is not configured, then an interface IP takes priority. This field ensures that the full sequence of DD, or database descriptor packets, is received in the database synchronization process. This sequence number is set by the master. And then we have the LSA header. This header lists some or all of the headers of the LSA in the originator's link state database. The header contains enough information to uniquely identify the LSA and the particular instance of the LSA. Next, we have Type 3, or the link state request. If after receiving a DD, or database descriptor packet, the neighbor router found that the LSA advertised by an adjacent router is not in its database, then this LSA is requested. The link state request packet fields are as follows. OSPF header. This header is 24 bytes long. The link state type. This field contains the LSA type number, whether it is LSA type 1, 2, 3, 4, or 5. Types of LSAs is discussed later on in this section. Then we have link state ID. This field is type dependent on the LSA header. And we have advertising router. This field contains the router ID of the router that originated the LSA. And then we have Type 4, the link state update. The link state update contains multiple LSA's information and transmitted between the designated router and other designated router, or BDRs. The link state update packet fields include OSPF header, which is 24 bytes long, a number of advertisements field. This field specifies the number of LSAs included in this packet, the link state advertisements, the full LSAs as described in OSPF LSA format. Each update can carry multiple LSAs, up to the maximum allowed packet size for the link. And then we have Type 5, link state acknowledgement. Once the router receives a Type 4 packet, it will send back an acknowledgement as the link state acknowledgement packet. This acknowledgement is sent as a unicast. The link state acknowledgement packet types are OSPF packet header and LSA header, which contains a list of LSA headers. So let's discuss one point here which people are often confused with. What is the significance of these two multicast IP addresses? We have 224.0.0.5. This is used to send OSPF messages to all OSPF routers on the same network. The address is used for hello packets. The designated router and backup designated router use this address to send link state updates and link state acknowledgement packets. And then we have address 224.0.0.6. This can also be referred to as all designated routers. This is used to send OSPF messages to all OSPF DRs and BDRs on the same network. Now let's talk a little bit about forming an adjacency. The adjacency is formed to optimize the network and to limit the LSA flooding. The basic adjacency criteria is used to elect the DR and the BDR. There are 7 steps to the adjacency process as shown here in this diagram. So let's describe each of the 7 steps. First, we have down. OSPF event has not started. Then we have init, or initialization. The hello packet is sent, but bidirectional communication has not yet started. Then we have the two-way. Bidirectional communication has started, but the election process has not yet started. Then we have EX start. Which router is master according to the RID, and which is the DR or BDR according to the highest priority or RID, and who is responsible for database synchronization with the start of the sequence number. Then we have the exchange. The LSA exchange happens between the routers, and if any LSA header received is unknown, then the complete information is requested. Then we have loading. The router finished transmitting its database, but is still receiving the database from the other router. And then we have full. Database is fully synchronized and the link can be advertised to the OSPF network. Note that the DR and the BDR election in OSPF is non-deterministic. Let's take a look at OSPF areas. Let's look at an example. What if the OSPF network grows larger? For instance, say you have 5 to 6 routers participating in OSPF. You really don't need more than one Area 0. Now, what if more routers are added into the network and the broadcast domain increases? More flooding within an area will start and the size of the link state database will begin to increase. So to control this, we divide the OSPF domain into different areas. By doing this, the LSA flooding and database size can be controlled. OSPF router types. These are the types of routers in an OSPF network. We have an area border router, or ABR. These routers fall into 2 areas, backbone and other area, and transmit LSAs between them. And then we have Autonomous System Boundary Router, or ASBR. This router gets the routing information outside the OSPF domain, or from other routing protocols like RIP or static routes. And then we have a backbone router. This is the router with the link to the backbone area. It can also be an ABR. And then we have internal router. These are routers with all links in the same area. It can be a backbone router with links in Area 0 only. Types of areas. First we have intra-area. These are where routes are generated within the area. And then we have inter-area, routes generated from other areas, say from Area 1 to Area 0. And then we have external areas, routes generated from other OSPF processes or other routing protocols redistributed into the current OSPF instance. And we have stub areas. These are external area routes and are not allowed within the area. Only router LSAs, network LSAs, and summary LSAs are allowed in this area. No LSA 4s and no LSA 5s. Total stubby area. Default route from the backbone area is allowed, but no LSA 3, 4s, or 5s are allowed. And then we have not so stubby area. Unlike stub area, the NSSA allows external routes to be flooded in this area. These allow type 1, 2, and 3 LSAs, and then leak into other areas. Type 4 and Type 5 LSAs are not allowed in this area. Note that the Junos OS allows you to also restrict Type 3 LSAs in a not-so-stubby area using the No Summaries configuration option. Just remember that you cannot configure an area to be both a stubby area and a not-so-stubby area. So let's talk a little bit about types of LSAs. First of all, we have router LSA or Type 1. This is within an area, so the prefix is advertised by all routers and interfaces within an area. Then we have network LSAs or Type 2s. LSAs originated from designated routers or other OSPF routers within an area. Then we have summary LSAs or Type 3s. originated by ABRs and is a collection of LSA-1 and LSA-2. When those LSAs are injected into other areas, their LSA type never changes, but the cost and advertising router does change. This is an inter-area. And then we have ASBR summary LSA, or Type 4. This is sent by an ABR router to find the RID of the ASBR router. In short, they are originated by the ABR to describe the RID of the ASBR. Note that like ASBR summary, LSAs are re-injected into different areas. The LSA type never changes, but the cost and advertising router details do change. Now we have external LSAs, or Type 5. Originated by an ASBR, these originate from an ASBR and are redistributed to the external routing protocols like RIP, BGP, or static routes into OSPF areas. The external routes are not added with the cost of ASBR and marked as Type 2 routes, but these can be changed to Type 1. And then we have not-so-stubby area external LSAs. These are external IP prefixes redistributed in a not-so-stubby area. These are very similar to external LSA types, but the key difference is that the routes from other areas are not allowed. In addition to the LSA types already discussed, the OSPF specification also includes the following LSA types. These are out of the scope of this material, but we're just going to mention them here. We have multicast OSPF LSA, or Type 6. We have external attributes LSA, or Type 8. We have opaque LSA, or Type 9. We have opaque LSA link scope, or Type 9. We have opaque LSA area scope, used for traffic engineering, or Type 10. And then we have opaque LSA AS scope, or Type 11. These aren't really covered in the exam and are not part of the course material, but I just wanted to make sure that I mentioned those as well. Now let's talk a little bit about what Junos supports as far as OSPF. OSPF version 2 and version 3 are supported, but the support of OSPF version 3 is limited and restricted to specific devices. Here are a few other supported features. Authentication. By default, OSPF version 2 authentication is disabled. The Junos OS supports simple authentication, message digest 5 or MD5 authentication, and IP security IPsec authentication. And we have summarization. The information of different prefixes or IP addresses will be summarized in a single LSA. And we have external prefix limits. By default, on Junos, there is no limit to the number of prefixes that can be exported into OSPF. You can use the prefix-export-limit statement to limit the number of external prefixes allowed in your OSPF network. And then we have bidirectional forwarding detection, or BFD. This protocol is independent of other routing protocols and can be used with OSPF to find a link failure detection. The BFD is explained in a little more detail in a later chapter. So what is RID? Every router is configured with a 32-bit field router ID. Make sure that this is not the IP address of the router, but just a name given to the router participating in OSPF. If the loopback interface is configured with a non-127/8 IP address, the Junos OS uses the address first. If a loopback interface is not configured, Junos uses the next suitable address, typically the dedicated management interface. So let's take a quick look at some configuration options for OSPF. So the first command that we're going to start with when we want to configure OSPF is the set protocols OSPF command. This is going to set the area, and we're also going to designate the interface we want to use, as well as a metric. If any loopback address is needed to be advertised, we can configure it like this. We can use the set protocols OSPF area, the area address or name, and then the interface LO0 or loopback. If we need to include any other interfaces or areas, we can configure them now with the set protocols OSPF, area, and then the area name, and then we can assign the other interface. So it's really easy to verify your OSPF configuration. The configuration of OSPF is fairly simple. So to verify our configuration, we can simply issue the show OSPF neighbor command. Now you're going to enter this command in operational mode, and this command is going to give you information about connected OSPF neighbors. This is how you're going to verify that your OSPF area is coming up and the routers are talking to each other. Now let's talk a little bit about some commands that are going to be useful when troubleshooting OSPF. We talked about trace options before in the JNCI Junos course, and that is what we're going to be configuring here. This will give us all the information we need about what's going on with OSPF. So the way that we would configure that is with the set protocols OSPF command, and then we're going to issue the trace options, file, and then we're going to specify a file name for that log, size, and then we're going to put a size limit on it. Then we'll issue the set protocols OSPF trace options flag all. This is going to flag all the events and log them. So we covered a lot of information about OSPF in this chapter, but the configuration of OSPF is relatively simple, and it's relatively simple to show that we have neighbors connecting and our OSPF network is coming together. And we also saw that it's fairly simple to configure the logging of OSPF so that if you do have problems, you have a log that logs everything that's happening and you can fairly easily figure out what's going wrong. Alright, so let's review. What is the purpose of OSPF LSAs? OSPF routers use LSAs to share information about their attached network with other neighboring OSPF routers. What are some of the benefits you might get by segmenting a large single-area OSPF environment into multiple areas? Well, you can restrict the size of an OSPF router's LSDB by incorporating multiple areas. In some types of OSPF areas, such as stub areas, totally stubby, and NSSA areas, only certain types of LSAs are flooded. What is the difference between ABR and ASBR? ABRs connect non-backbone areas to the backbone area, and ASBRs inject external prefixes into OSPF using redistribution policy. Note that an OSPF router can be an ABR and an ASBR simultaneously. List some common OSPF area types and their functionality. Alright, let's look at a list of some common OSPF area types and their functionality. There are several types of OSPF areas, including stubby, totally stubby, and NSSA areas. Stub areas do not carry external routes and cannot contain ASBRs. Totally stubby areas are stub areas that do not receive summary LSAs from the backbone, but rather receive a single LSA that represents a default route. NSSA areas allow external routes to be advertised from the area but are not received from other areas. It's also worth mentioning that the backbone area, area 0.0.0, is the area that all other areas connect to. And that's it for this section. We covered a lot of information, so if you feel the need to watch the video again, we recommend that you do. Now it's time to move on to the quiz and the next section. Thanks for watching.